This time we'll attempt to find the volume when the area between these two curves is revolved around the line y equals 3. Once again, I've enlisted the help of some graphing utilities to in advance paint you a picture of the cross section with the boundaries included. This is important information that sometimes you need to find for yourself, but you must employ pre-calculus methods to do so. And I've also used the excellent volume of revolutions graphing utility I found on the internet, the link to which I have in the description. So I once again recommend that you fool around with that for confirming your own problem-solving methods when you encounter this in your calculus course. But the thing that's different about this, as opposed to the very previous video I did, is that now we must revolve around a very particular line, y equals 3, and not just the x-axis, y equals 0. I'll start my thinking by assuming that the volume of the solid of interest by the washer method should be the volume of this orange area minus the volume of the red area, which will be blank space, as pictured here, sort of in orange and red. Well, what is the volume of a disk? Once again, the volume of a solid such as this one, the orange solid, given by all of this space, is the summation of the volumes of disks that stack up and fit inside it. Let's start talking about the volume of a singular disk represented by an arbitrary position along the x-axis. It is a cylinder whose volume is given by pi r squared h. Like last time, the h, so to speak, is given by an infinitesimally thin length along the x-axis. But the radius is where we have to be careful. The radius is given by this distance, but it is not the height of the function. It was in the previous problem, but this time it's going to be the value of the function y equals 6 minus 2x minus x squared minus 3 to represent the fact that we do not want to count everything that falls below this line, only the curved part above it. So that does most of the legwork in terms of solving this problem. This is the main difference. The volume of a singular disk will be pi 6 minus 2x minus x squared minus 3 squared delta x. And the volume of all the disks that come together to stack up and make this shape, that's disks with an S, plural, sorry about my handwriting there, will be the integral from negative 3 to 0 of pi 6 minus 2x minus x squared minus 3 squared dx. Let's do a similar analysis to the blank space I have over here in red. Kind of represent the volume of this cone-shaped thing. The volume of one of the disks that represents that shape will once again be given by pi r squared h. The h is a length along the x-axis. This time, the radius will be given by the function minus 3, the function x plus 6 minus 3. So the volume of our disk is pi x plus 6 minus 3 squared times delta x. I guess kind of silly not to have that. X plus 3 squared delta x. Looking at that, I could have combined those two as well. But the volume of all these red disks, a plurality of red disks, is the integral from negative 3 to 0 of pi x plus 3 squared dx. So we need to subtract orange space from red space. Oh, I'm sorry, red space from orange space. That means we have to do the integral from negative 3 to 0 of orange. You know what, let me go ahead and just combine the 6 and the negative 3 like I said I was going to. And minus the red integral. And this, by properties of integrals, simplifies into a single one, which I will not evaluate in this video. It can be expanded into a polynomial form. That would probably be the best way to solve it. It would kind of take a while, but we'll have the integral of this orange polynomial squared minus the red polynomial squared. The value of this integral, when evaluated, becomes just about 67.85. Such is the volume of this solid